Welcome back, viewers, to my physics channel. I am Dr. DORCAS NGIGI. Now we've been moving together from our first topic, that is floating and sinking. Then we started our second topic, that is thin lenses. So now this is our around 13th lesson. In the last lesson, we looked at how to derive the lens formula, and we applied it in one of the examples, because we said we want to determine from the image characteristics using ray diagrams. We were able to get the position of the image, but we could not get the exact object image size and the exact image distance. But from the lens formula, which we said is 1 over f equals to 1 over v plus 1 over u, where v is the image distance and u is the object distance. Using that formula, we were able, from the example that I gave in the last lesson, to determine not only the image distance, the exact image distance, but we are also able to determine its height. Okay? So today we are going to do another example, maybe 2 examples on the same, one on concave and another one on convex. Now, the other thing we are going to do, we are going to look at how else to determine this image distance and image size by graphical representation. We can put that information on a graph, and from the graph we can be able to determine the image distance and the image size. So please welcome, let's get started. Okay, so here we go. So let's take another example, or let's just take yesterday's example and use that example now on a diverging lens. So we said, example, an object of height 2 meters was placed in front of a diverging lens of focal length 10 centimeters. Okay, so determine 1, image distance, Roman 2, image height, Roman 3, let's say magnification, and Roman 4, nature of the image. Okay, so this time we are using is the same question of an object of height 2 meters, which was placed in front of a diverging lens of focal length 10 centimeters. Okay, now we want to determine the image distance, the image height, the magnification, and the nature of the image using that lens formula. So 1 over f is 1 over v plus 1 over u. This is the lens formula. So we want to determine that using the lens formula, and then we are going to use this the graphical method to determine the same. Okay, so let's get started. So let's say we have this. So we have 1 over f. So let's start by writing what we have. So we have f. Now f is 10 centimeters, but negative. Now, why are we saying that f is negative? Remember, we are using a diverging lens, and we said the focal length, the focal point of a diverging lens is virtue. Rays do not go through the focal length, the focal point, neither do they come from the focal point. They look like they want to go through the focal point, and they look like they are coming from the focal point after refraction by the diverging lens. So that focal point or principal focus is virtue. It is not true. Now, in these lenses and in mirrors, we looked at this in curved mirrors, we use the convention that is called the real is positive. Real is positive convention. What does that mean? Anything that is real is going to be given positive sign. Anything that is virtue is going to be given negative sign. So for example, since I'm using a diverging lens, the focal point or the focal length of a diverging lens is virtue. So it is going to be minus. Remember yesterday when we calculated using a converging lens, that is a biconvex, we used F as positive 10. Why? Because the focal point of a converging lens is a true focus. Rays pass through it as incident rays, and they also are refracted through it as after refraction by the lens. So it's a true focus. So it's real is positive convention. So we are using real is positive convention, don't forget. So I'm going to use it as negative 10. So U, image object distance, that also we have an object of height 2 meters was placed in front of a diverging lens or focal length. So it was placed 15 centimeters in front of a diverging lens of focal length 10. So the object distance, we are still using the same example of yesterday. The only thing that has changed is the type of lens, okay? So is 10, that is 15 centimeters. So that is what we have. So what we are calculating there is the image distance. Now from our lens formula, 1 over F equals to 1 over V plus 1 over U. Then we can use that here. So we can say, now put what you need as the subject. 1 over V equals to 1 over 10. Remember it's negative. It's negative. Centimeters minus 1 over 15 centimeters. Okay. Now from there we get the LCM. That is going to be 30 centimeters. 10 centimeters goes to 30 centimeters 3 times. So 3 times 1, that is, and it's 3 times negative, so it's minus 3. 15 centimeters goes to 30 centimeters twice. So 2 times negative 1, that is minus 2. Okay, so 1 over V equals to minus 3 minus 2, that is minus 5 over 30 centimeters. Now remember, we are not looking for 1 over V. We are looking for V, okay? So I need to get the reciprocal of this, which will be equal to the reciprocal of that, don't forget. So V over 1, of course, is going to be 30 centimeters divided by 5, okay? So V is going to be minus 6 centimeters, okay? So what does minus 6 centimeters stand for? Why minus? Now remember, there are two sides of a lens. There is a side where we have the object, and there is the other side of the object, the other side of the lens, where for a concave mirror, of course, we are supposed to form true images. That side is positive, okay? But the side where the object is, if the image forms on that side, then that side is negative. Just like in a number line, that side is positive, the other side is negative. So that is why it is negative, because the image and the object are forming on the same side. The image and the object are forming on the same side. Now with that, so negative only stands for the direction. The negative here is not a magnitude, it stands for the direction. The direction where we have the object is negative if the image is in that direction. But it is positive if the object is in the opposite direction. So negative does not stand for magnitude, it stands for the direction in our case. Okay, so we have calculated the image distance. Now, we calculate magnification, for us to be able to get image height, we can use magnification. We say magnification is V over U, that is image distance over object distance, is also equal to image height over object height. Okay, which is now image distance is 6 centimeters. I ignore negative because negative just gives direction, it's not magnitude. Magnitude is 6 centimeters divided by 15 centimeters. Our object distance should give us height of image over height of object, which is 2 meters. 2 meters, okay? So of course, to get height of image, I want to cross multiply, so that is 2 meters multiplied by 6 centimeters over 15 centimeters. Of course, that comes up. So that is equal to 12 meters over 15. So height of image equals to, that is by 3, that is 4, and that is 5. 4 over 5, which is approximately 0.8 centimeters. Did I do there? Let me go back. 0.8 meters. Okay. So if we look at height of image, so we have calculated image height. Of course, we expect the image height to be smaller than the object height because we are using a diverging lens. We said when you're using a diverging lens, all the images have the same characteristics regardless of the object position on the principal axis. And one of the characteristics is that object, that image is going to be virtue. And because it's virtue, that's why it is forming the same side as the object. Being virtue means it is also upright. We're also saying it is going to be smaller than our object, and it is going to form the same side as the object, and more, it will fall between the principal focus and the optical center. Please review that for better understanding in the previous lesson. Okay, so the other thing we're going to look at is magnification. So magnification, we have the formula there is V over U, or simply height of image over height of object. So if we do that, then what we get, V is 6 centimeters divided by U, which is 15 centimeters. So which is equal to, remember magnification is a ratio, it has no units. So by 3, that is 2 over 5. That's what? 0.4. So magnification is 0.4, meaning the image is smaller than the object. Remember, for magnification, we are measuring, is a measure of what is the size of image relative to the size of the object. So if magnification is 1, then the image and the object have the same size. If magnification is greater than 1, then it means the image is magnified, meaning it is bigger than the object. If it is less than 1, then we expect the image to be smaller than the object. And in our case, because we are using a diverging lens, and all images are diminished, meaning they are smaller than the object, now from the magnification, then we have that. Finally, we look at the nature of our image. Of course, we have already talked about that. Magnification is 0.4, meaning it is smaller than the object. The distance, image distance is negative, meaning it has formed the same side as the object. And all that means it is virtue, and so we expect it to be upright. So 1, it is virtue. So 2, it is upright. 3, so forms same side as the object. So those are some of the characteristics of that image. Upright, it is virtue, forms same side as the object, and it is diminished. Okay, so we have looked at our second example. So I can call this example 2. The first one, we used the same, but using a converging lens. Now we have done the same example, but this time using a diverging lens. Now, what if I want to use, I don't know the lens formula, and I want to use a graph paper. Now, I have drawn something here, which looks like a graph, okay? And so we are going to use that just for better understanding of our concept. Now in this one, we're going to assume we are using a converging lens. Let's assume we are using a converging lens. Now if you're using a converging lens, then the focal length is going to be that. Now we have to draw to scale. Let's say the horizontal, I don't know where to rub. Didn't want to rub this. Try to so the horizontal scale, so 1 centimeter to represent 10 centimeter. So we're going to take one small box from here to here, one small box to be our 1 centimeter, okay? To stand for the 10 centimeters of our actual measurement. Then the vertical one, since we are using height of object in meters, let's say we have horizontal, that is vertical scale. Let's say 1 centimeter equals to 1 meter, okay? Because we have 2 meters, so on the vertical, we can choose 1 centimeter, one small square to represent 1 meter, okay? So let's put that information there. So the first thing, we need to show the type of lens that we are using. And so let's put it that way. So I am using a converging lens. I'm trying to be accurate. Okay, have that is my lens. Then the other thing I'm going to have is the principal axis. Let me check as my, I'm trying to follow these lines. It's not very easy. Okay, now we have the focal length as 10. Okay, so we have said 1 centimeter to represent 10. So I have F there and there, and of course if that is 10, of course I have 2F, 2F. Remember, this is our optical center, and the distance from the optical center to the principal focus is equal to the distance from the principal focus to the center of curvature, which is 2F. So if this is one box, that is 2 boxes for center of curvature, and 1 box for the principal focus. Okay, so we have F, we have put it 10 centimeters, so 10, 10, and 20, 20. Then the other thing we have is the object, which is 15 centimeters. So my object is somewhere at the center here, that is 10, this is 20, so it's around there. And the height is, on the vertical, we are using 1 centimeter to represent 1 meter. So I'm going to go up 2 boxes, that is 2 meters. So somewhere there. Okay. So from there, I'm going to follow the rules. We know the rules by now. And so what does the rules say? The first ray which passes through, let's use the one that is parallel to the principal axis, that one. From the tip of the object, that ray should be refracted so that it passes through the principal focus. So we have that ray is moving that way. Okay, so now the other ray is the ray that strikes the lens, passing through the optical center, and that one we said should pass undeviated. So we have this. Something like that. Okay, now where the 2 rays meet, that is where we form our image. That is where we form our image. I think that one is very correct. something like that. And so where the two lines intersect after refraction by the lens, the two lines of course intersect, and they intersect somewhere here. It's a bit better than the previous one. And so we draw a straight line on at that point going up. Something like that. Okay. So I hope it gives you a rough idea on how to use your graph paper. Remember this information, you are using it on a graph paper. Okay, now with that, now we are not using the mirror formula, we are simply putting that information on a graph paper, and then we are following the rules. A ray that is parallel and close to the principal axis should be refracted through the principal focus. A ray that goes through the principal focus, a ray that passes through the optical center, that one should pass undeviated. Don't forget these rules, because on a graph paper without the lens formula, you have to remember those rules. So now from there, now we can answer the questions. Now if we were using a converging lens, remember the question, yesterday's question. So if we were using a diverging lens, then image distance V should be equal to what? That is 1, 2, 3 boxes. So that should give us one box in the horizontal scale. 1 centimeter is 10 centimeters, so that is around 30 centimeters. So the other thing is image height. Image height, we have gone how many boxes? 1, 2, 3, 4. And 1 centimeter is 1 meter, so that is around 4 meters. Now if we look at magnification, then magnification equals to, that is 30 centimeters, image distance over 15 centimeters, object distance, which is 2. Or it is 4 meters, image height, over 2 meters, object height, which is 2. And of course, with this, the nature is straightforward. The object, the image is, remember this is the object, that's image. The image is true. You see it is intersection of true refracted rays. So we expect it to form on a screen. So it's a true image. Because it's true, it is inverted. It is magnified. It is bigger than our object. As you can see, it is forming on a screen, and it is bigger because the object is between 2F and F. So it forms behind C, behind 2F, and it must be bigger than the object. It's one of the magnified images that we form using a converging lens. Okay, and the other thing, it forms behind the center of curvature 2F. So these answers are the same answers we got yesterday when we did that question using the lens formula. So you can do that. So I give you this as an assignment. Use the one for converging lens. Use your graph paper to do the one that we have just done right now using a converging lens. So that brings us to the end of our lesson. I hope you enjoyed the lesson. Please don't forget to like and subscribe. And I also hope to see you in my next video. For now, goodbye.